Welcome to the ultimate guide for developers who want to transition into a system architect role. If you're a developer who's been writing code for years and want to level up to designing entire systems, this video is for you. Being a system architect isn't just about knowing more technologies. It's about thinking differently. You'll learn to see the big picture, make trade-off decisions, and design systems that scale, perform, and evolve over time. In this video, we'll cover everything you need. Design patterns and principles, scalability, microservices, API design, database architecture, cloud infrastructure, security, system design practice, and the soft skills that set great architects apart. So what exactly does a system architect do? As a developer, your job is to write code that works. As an architect, your job is to design systems that work at scale, under real-world constraints. A system architect is responsible for big-picture thinking. You define how components interact, what technologies to use, and how the system will evolve over years. You create blueprints, not just code. Think of it like this. A developer is a skilled carpenter building a room. An architect designs the entire building, deciding where the rooms go, how the plumbing runs, and how many floors the structure can support. One of your most important skills is trade-off analysis. There's never a perfect solution. You must balance performance versus cost, consistency versus availability, simplicity versus flexibility. Every decision has consequences. You also serve as a bridge between business and engineering. You translate business requirements into technical designs. You explain technical constraints to non-technical stakeholders. This communication skill is as important as your technical knowledge. The key areas you need to master are design patterns and principles, scalability strategies, distributed systems, data architecture, cloud infrastructure, security, and system design methodology. Let's dive into each one. Design patterns and principles are the foundation of good architecture. Let's start with solid, the 5 principles every architect must internalize. S is single responsibility. Every class, module, or service should have one reason to change. If your user service handles authentication and email sending and profile updates, it violates this principle. O is open-closed. Your system should be open for extension but closed for modification. Use interfaces, plugins, and strategy patterns so new features don't require changing existing code. L is Liskov substitution. Any subtype should be usable wherever its parent type is expected. If your code breaks when you swap a subclass, your inheritance hierarchy is wrong. I is interface segregation. Many specific interfaces are better than one fat interface. Don't force classes to implement methods they don't need. Split large interfaces into focused ones. D is dependency inversion. High-level modules should depend on abstractions, not concrete implementations. This is the foundation of dependency injection and plugin architectures. Beyond solid, you need to know key design patterns. Creational patterns like factory and builder control how objects are created. Structural patterns like adapter and facade simplify complex interfaces. Behavioral patterns like observer and strategy manage how objects communicate. And architectural patterns like CQRS, event sourcing, and hexagonal architecture shape entire systems. These aren't academic exercises. They solve real problems you'll face every day as an architect. Scalability is the ability of your system to handle growing amounts of work. As an architect, this is one of your primary concerns. Let's break down the key strategies. Vertical scaling means adding more power to your existing server. More CPU, more RAM, more storage. It's simple but has hard limits. You can't infinitely upgrade a single machine, and it creates a single point of failure. Horizontal scaling means adding more servers. Instead of one powerful machine, you use many regular machines behind a load balancer. This is how companies like Netflix and Google scale to billions of users. Caching is your best friend for performance. A CDN caches static assets close to users. Redis or memcached cache frequently access data in memory. Application-level caching avoids repeated computations. Caching can reduce response times from 200 milliseconds to under 5 milliseconds. Load balancing distributes traffic across your servers. Common strategies include round-robin, least connections, and consistent hashing. You need to understand when to use each one. Asynchronous processing is critical for scalability. Instead of doing everything synchronously in the request path, offload heavy work to message queues. RabbitMQ, Kafka, and SQS let services process work independently at their own pace. Remember the key metrics. Latency is how fast a single request completes. Throughput is how many requests per second your system handles. Availability is your uptime percentage. A good architect designs for all three. One of the biggest architectural decisions you'll make is choosing between Monolith and microservices. Let's understand both deeply so you can make the right call. A monolith is a single deployable unit. All your code lives in one application. It shares one database and one process. Monoliths are simple to develop, test, and deploy. For most startups and small teams, a monolith is the right choice. Microservices split your application into small, independent services. Each service owns its data, can be deployed independently, and communicates over the network. This gives you technology flexibility and independent scaling. But microservices come with serious costs. You need service discovery, distributed tracing, network failure handling, data consistency across services, and a mature DevOps practice. Don't underestimate this complexity. The golden rule is, start with a well-structured monolith. Extract services only when you feel real pain. If one part of your system needs to scale independently, or if different teams need to deploy at different speeds, that's when microservices make sense. Domain-driven design gives you the tool to find service boundaries. Bounded contexts define where one model ends and another begins. Each bounded context can become a microservice. For communication, use synchronous calls like REST or gRPC for queries where you need an immediate response. Use asynchronous events for commands and state changes. This event-driven approach keeps services decoupled and resilient. API design is how your system components talk to each other and to the outside world. As an architect, you need to master multiple communication patterns. REST APIs are the universal standard. They use HTTP methods, resource-based URLs, and are stateless. REST is great for public APIs, web frontends, and mobile apps. Follow conventions like proper status codes, pagination, and versioning. GraphQL lets clients request exactly the data they need in a single request. Instead of multiple REST endpoints, you have one endpoint with a flexible query language. It's perfect for complex UIs with varied data needs. gRPC uses protocol buffers for binary serialization and supports streaming. It's significantly faster than REST and ideal for service-to-service communication within your infrastructure. Message queues like RabbitMQ, Apache Kafka, and Amazon SQS enable asynchronous communication. A service publishes a message and moves on. Another service consumes it when ready. This decouples services and improves resilience. Event-driven architecture takes this further. Services emit events when something happens. Other services react to those events. This creates a reactive system where components are loosely coupled. As an architect, choose the right tool for each interaction. Don't use REST for everything. Don't use Kafka when a simple HTTP call would do. Match the communication pattern to the use case. Database architecture decisions have the longest lasting impact on your system. Let's understand your options and when to use each one. Relational databases like PostgreSQL, MySQL, and SQL Server provide ACID transactions, structured schemas, and powerful SQL queries. They're ideal for transactional data where consistency matters. Most applications should start with a relational database. NoSQL databases offer different trade-offs. Document stores like MongoDB provide flexible schemas. Key-value stores like Redis offer blazing fast lookups. Column family stores like Cassandra handle massive write workloads. Graph databases like Neo4j model complex relationships. Sharding splits your data across multiple database servers. You might shard by user ID, region, or date range. This enables horizontal scaling but adds complexity to queries that span multiple shards. Replication creates copies of your database. A primary replica setup lets you scale reads by directing queries to replicas while writes go to the primary. This also provides high availability. The CQRS pattern separates read and write models. Your write side uses a normalized relational database. Your read side uses denormalized views optimized for queries. This lets you optimize each side independently. The CAP theorem states that in a distributed system, you can only guarantee two of three properties: consistency, availability, and partition tolerance. Since network partitions are inevitable, you're really choosing between consistency and availability. Modern system architecture is inseparable from cloud infrastructure. You don't need to master every service, but you need to understand the core building blocks. The three major cloud providers are AWS, Azure, and GCP. Each offers compute, storage, databases, and networking. Learn the concepts, and you can work with any provider. Docker containers package your application with all its dependencies into a portable unit. A container runs the same way on your laptop, in CI, and in production. This eliminates the "it works on my machine" problem. Kubernetes orchestrates your containers at scale. It handles autoscaling, rolling deployments, self-healing, service discovery, and load balancing. It's complex to learn but essential for running microservices in production. Infrastructure as code tools like Terraform, Pulumi, and CloudFormation let you define your entire infrastructure in version-controlled files. No more clicking through cloud consoles. Your infrastructure is reviewable, repeatable, and auditable. CI/CD pipelines automate your build, test, and deployment process. GitHub Actions, Jenkins, and GitLab CI can automatically run tests, build containers, and deploy to production on every merge. As an architect, design for failure. Use multiple availability zones. Implement health checks and circuit breakers. Plan for disaster recovery. The cloud gives you the tools, but you have to use them intentionally. Security architecture is not optional. It's a core responsibility of every system architect. Let's cover the essential security patterns you must know. Zero trust architecture means never trust, always verify. Every request is authenticated and authorized, even within your internal network. Don't assume that traffic from inside your VPC is safe. Authentication verifies who someone is. OAuth 2.0 and OpenID Connect are the industry standards. JSON Web Tokens carry identity claims between services. Always validate tokens on every request. Authorization determines what someone can do. Role-based access control assigns permissions to roles. Attribute-based access control makes decisions based on attributes like department, time, or location. Encryption protects data in two states. In transit, use TLS everywhere, even between internal services. At rest, encrypt your databases, file storage, and backups using AES 256. The OWASP Top 10 lists the most critical security risks. SQL injection, cross-site scripting, broken authentication, and insecure deserialization are attacks you must prevent. Defense in depth means multiple security layers. A web application firewall blocks malicious traffic. Network segmentation isolates services. Application-level validation catches bad input. Each layer protects against different threats. Now let's put it all together with system design methodology. This is what separates a developer from an architect. Step 1. Clarify requirements. Don't jump into designing. Ask questions. What are the functional requirements? What are the non-functional requirements like latency, throughput, and availability? Step 2. Estimate scale. Do back-of-envelope calculations. If you have 100 million users with 10% daily active, that's 10 million daily users. If each makes 10 requests per day, that's about 1,200 requests per second. Step 3. Create a high-level design. Draw the main components. Clients, load balancers, application servers, caches, databases, and message queues. Define the APIs between them. Step 4. Deep dive into critical components. Design the database schema. Choose your caching strategy. Define the data partitioning approach. Pick the most challenging component and go deep. Step 5. Identify bottlenecks and single points of failure. What happens when the database goes down? What if traffic spikes 10 times? Walk through failure scenarios and design mitigations. Step 6. Address trade-offs explicitly. Every design decision has pros and cons. Strong consistency slows down writes. Caching introduces stale data. A great architect communicates these trade-offs clearly. Practice by designing real systems. Design a URL shortener, a chat application, a newsfeed, or a video streaming platform. Each one teaches different architectural patterns and challenges. Technical skills alone won't make you a great architect. The soft skills are equally important, and often the hardest to develop. Communication is number one. You must explain complex systems simply. Use diagrams, not just words. Learn the C4 model for architecture diagrams: context, containers, components, and code. Trade-off analysis is your daily bread. There is never a perfect solution. Your job is to evaluate options, articulate the pros and cons of each, and recommend the best fit for your specific context. Stakeholder management means aligning engineering, product, and business on technical direction. Learn to speak the language of each group. Engineers care about code quality. Product cares about features. Business cares about cost. Mentoring and growing the team is a force multiplier. Share knowledge through design reviews, tech talks, and pair programming. When you help 10 developers make better decisions, you have 10 times the impact. Finally, develop technical vision. Think 2 to 3 years ahead. How will the system need to evolve? What technical debt needs to be addressed? Create a technology roadmap that guides the team. Remember, the transition from developer to architect is not a promotion. It's a career change. You trade writing code for designing systems, individual contribution for team impact, and solving problems for preventing problems. Congratulations! You now have a complete roadmap for transitioning from developer to system architect. Let's recap the key skills you need to master. Design patterns and solid principles form your foundation. Scalability, microservices, and API design help you build distributed systems. Database architecture and cloud infrastructure are your building blocks. Security and system design methodology tie it all together. And soft skills are your secret weapon. This journey takes time. Start by making architectural decisions in your current projects. Read system design case studies. Practice whiteboard design. Most importantly, think beyond the code and see the whole system. If this video helped you, please like and subscribe for more architecture content. Your architect journey starts now.